Hey everyone, welcome back to a new lesson. So in the previous lesson we were focusing on polar molecules and the intermolecular forces between water molecules and other compounds that are also polar. We said that when you take a polar compound and you put it inside water, or you take salt for example, which is a ionic lattice, an ionic compound, it will dissolve inside the water because of the intermolecular forces, the dipole-dipole and the ion-dipole moments that occur between the following molecules. But now we are going to talk about a new molecule, a new biomolecule, which is one of our 4 biomolecules that form most of the things in the biochemistry of our body and many different organisms' body. It's called lipids and fatty acids, and I'm sure you heard of it. And on this lesson, we are going to talk about how we recognize fatty acids, what are the properties of fatty acids, and how we name fatty acids. And on the next lesson, I'm going to proceed and teach you guys some new chemical properties of fatty acids and some extra ways that you should know how to recognize and name fatty acids. So let's begin. In the previous video, we were talking about polar compounds that are being dissolved in water. The polar compounds form intermolecular forces with water because they are so polar themselves, and the interaction, the polarity, is able to react with the hydrogen bonds. This compound that you put inside water and it's able to dissolve inside the water is called hydrophilic compound. Hydro for water and philic loving. So you have hydrophilic compound, polar compound, which reacts with water. On the other hand, we have lipids that we are going to study today. Lipids are mainly non-polar. And because they are mainly non-polar, we said that lipids are hydrophobic. Phobic is fearing from something. So hydro water, phobic, the fear of something. If you take oil, for example, and you put it in a glass of water and you stir it around, unlike the sugar and the salt, this time oil won't dissolve inside the water, and it will form a specific layer of oil and you have the rest water. It won't dissolve together, which is very important to understand. This is the properties when it comes to non-polar compound inside water. Water won't be able to dissolve it because it won't be able to make hydrogen bonds between the molecules. Therefore, it won't be able to interfere the connections between the intermolecular forces of the compound. Therefore, you won't be able to dissolve non-polar compound inside water or any other polar solvent for this example. Fatty acids look as the following. They are built from 2 main things. And I want to give you a second to pause this video and to use the tools I gave you, the videos before, and try to analyze the following molecules yourself. So what do we see here? And I hope you actually pause the video and analyze the following molecule yourself. What do we see here? First of all, I see a functional group. We already studied this functional group when I mentioned in the common functional groups in the few videos ago. We can see the carboxylic acid over here. And we also see OH, which means that this part of the molecule can form hydrogen bonds. What we also see is a very long hydrocarbon that is being connected to the carboxylic acid. This part is also very important, and this part is our very hydrophobic zone of the molecule. When you have a molecule that contains a part hydrophilic and part hydrophobic, we call the molecule amphipathic. And this is a very good definition to remember. So by now we understood what are hydrophobic and hydrophilic molecules, and we understood what is an amphipathic molecule. Amphipathic molecule is when you have one molecule which has 2 different zones, of one hydrophobic and the other one hydrophilic. However, because the vast majority of the fatty acid is usually hydrophobic because the hydrocarbon is way bigger than the carboxylic acid zone. We said that fatty acids are mainly hydrophobic. So the following molecule can vary in many different ways. The main way that it can vary is the length of the hydrocarbon that you see here and the saturation of the hydrocarbon. So here we can see that the hydrocarbon is fully saturated, which means it doesn't contain any double or triple bond, as we said in the previous video. It's completely saturated with hydrogen, and we will understand how it comes, what is the significance of being an unsaturated or saturated fatty acid in the second part of this video. But just now remember that this part of the molecule, the hydrocarbon, can be with different amount of triple or double bonds. So for this example, you can see that we don't have any double bonds. But if I will take, for example, the following 3 fatty acids that we are going to name in a few seconds, you will see that you have 1 double bond, or here you have 2 double bonds, or here you have even 3 double bonds. The degree of saturation help us to define the name and find the name of the fatty acid, and also assume its properties. So we said 1, it can vary in length of the hydrocarbon. 2, it can change the degree of unsaturation and amount of double or triple bonds inside the molecule can vary as well. And 3, as we said from our previous video, when you have different properties of the molecule, when you have different functional groups, you will have different properties of the molecule. And in our case, when we have more saturation of the molecule, the melting, boiling and fluidity, melting point, boiling point and fluidity of the fatty acid will change as well. And in the next part of the video, I'm going to actually explain you guys how the fluidity, melting point and boiling point are being affected by the fact that you have double bonds inside the molecule. So, the next thing I would like to talk about is the simple way that we name the following molecule, the following fatty acids. Do you remember that I briefly mentioned the fact that different hydrocarbons, alkanes, alkenes and alkynes have different names? And we can name them based on the amount of carbons in the longest chain, the longest backbone. So in this fatty acid, we have 16 carbons. 16 is hexa for 6 and decane for 10, so 16. But we also have the carboxylic group. So what we do when we want to name a fully saturated fatty acids with specifically 16 carbons in our case is we take off the E of the alkane in our case and we put oic for the fatty acid, the fat part, and acid. Let's take a moment and actually understand and see what is the significance of the name. So hexadecane is the hydrocarbon part. Oic is also the hydrocarbon part. It's very important to remember. Oic is for the fat part itself. Acid, on the other hand, is for the carboxylic acid functional group that you are going to see in all fatty acids, because fatty acids are defined by hydrocarbon connected to a carboxylic acid group. The next 3 are a bit more complicated to name. So the nomenclature is as the following. This one has 1 double bond. This one has 2 double bond. And this one has 3 double bonds. In the next video, I'm going to explain about how to actually name based on the specific position of the double bond inside the molecule. But for now, know that when you have a single one, we said it's hexa, decanoic acid. When you have two, it's hexa, decadi for two, noic acid. When you have three, it's hexa, decatrinoic acid. So we mentioned the amount of unsaturation, the amount of double bonds we have. We mentioned the fact that you have the hydrocarbon, which represents the fat part of the fatty acids, the hydrophobic part, and we mentioned the acid, which is the carboxylic acid part. In the next video, I'm going to explain exactly what are the properties, why it is so important to have the knowledge about the unsaturation and the double bonds inside the molecule. And we're also going to mention how to name the molecules based on the exact position of the double or triple bonds. One last thing to mention is that, do you see the following way to write the ratios between the amount of carbons you have in the backbone and the double or triple bonds? It's a very important way to write and to mention any fatty acid composition, and it's a well-known way. So remember the following ratio, the following way to write it. This part is the amount of carbons you have in the longest backbone, which is the fatty acid itself, the hydrocarbon, and the other part is just the ratio of how many unsaturated points, how many triple or double bonds you have along these 16 carbons. So I hope it makes sense. Make sure to comment your questions down below, and in the next part of the video I'm going to explain how to exactly see the properties, deduct the properties of the following fatty acids, and how to name them precisely based on the position of the double or triple bonds. I will see you next time.